Okie dokie. So we're talking today about how we got the periodic table and why it is so incredibly awesome. The periodic table is fantastic. You have probably seen it just in passing. In this class, we haven't used it a lot until now, but you looked at it a little bit in physical science. You should have heard the story of its production from Dmitry Mendeleev already. You will read about that in your book as we do some more activities with the book as we go forward in this chapter. But the reason we introduced the periodic table to you now is because it's all about electron arrangements. And that's what we're talking about this week in this chapter is electron arrangements. So we talked about already that an atom is made up of electrons, protons, and neutrons. And we talked about the fact that elements have atomic numbers. And you've heard all of this before. Now I'm going to teach you how this periodic table displays all of that information and also displays the electron configuration of elements. If you can read the table, you know an element's electron configuration already, and you don't have to stress about memorizing what order things happen in, and all of the like 1s and the 2s and the 2px and all that you can read straight from here, which is going to make your life a lot easier. So that's what we're getting into here today. Elements are all given a 1 or 2 letter symbol based on their Latin name. So sometimes the Latin name for an element starts with the same letter or letters that it starts with English, so that's helpful. So like bismuth is Bi, and that's helpful. Copper is C. Now I'm blanking. CO. No, that's cobalt. Cobalt is CO, and that's the the way it starts in English. Nickel and I, that's the way it starts in English. But then you look at something like lead, and lead is PB, and you're like, what? PB? That's not how you spell lead in English. It's not lead, right? But that's because we use a Latin name for these elements, and sometimes the Latin name and the English names are the same letters, so it's handy sometimes. Not so much. Mercury, Hg. Mercury is not mercury. And so you have to just kind of be at peace with the fact that sometimes the letters don't make sense for the element. Sodium is Na. But you'll use these enough that you'll become familiar with them. I am not going to make you memorize the periodic table. Some chemistry teachers want you to memorize the periodic table. We give you periodic tables in your book. There's always going to be a periodic table up here when we're doing something with the periodic table. You should be familiar with where to find things, but I'm not going to make you like, here's a blank periodic table, fill it in. I had to do that when I took high school chemistry, and I had no idea why he was making me do that, because there's periodic tables everywhere. Why do I have to memorize this? Be familiar with where things are, but you don't have to have it, in your brain as lodged in there or part of you. So elements are given a 2-letter symbol, and we use that symbol all the time to refer to element equations and things of that nature. The number above the element tells you how many protons and therefore how many electrons in a normal state the atom has. So, for example, beryllium, Be, is element number 4. And what that means is that there are 4 protons. If an atom has 4 protons, it is beryllium. If an atom does not have 4 protons, it is not beryllium. You can change the number of neutrons, you can change the number of electrons, and you still have beryllium. But if you change the number of protons, it's not beryllium anymore. So it's the number of protons that make an element what it is. It's because it has 4 protons that it behaves like beryllium, okay? It's because it has 3 protons that it behaves like lithium. It's because it has 1 proton that it behaves like hydrogen. The chemical and physical properties of an element are determined by the number of protons in the nucleus. Number of neutrons and number of electrons can change. Now, in an electrically neutral atom, where it doesn't have a charge, it's a normal state for the atom, then it also will have that many electrons, because remember, there are the same number of electrons as there are protons. If there are 4 positive things in the nucleus, there must be 4 negative things around the outside to balance it out. But you can change the number of electrons when an element binds and forms an ion and things of that nature. So it's not always that the number of electrons is the same as the number of protons, but in a natural neutral state where it doesn't have a charge, the number of electrons equals the number of protons. Okay. The chemical properties roughly line up in columns that we call families. So more or less, everything in this column behaves the same way. And everything in this column behaves the same way. And then over here it gets a little bit fuzzy, but more or less things still line up in columns. And so an element has similar chemical properties to the elements above and below it. Bromine acts a lot like iodine. Matter of fact, bromine and iodine are both used in medicine to kill things and clean wounds. And chlorine kills things really well. Chlorine kills things so well that we don't use it as medicine because it would kill you. But it is used in pools to kill algae and bacteria and things like that. But you can also have bromine in pools, and then it doesn't change the flavor of the water, and people don't like have their eyes burning as much. So all of these things behave similarly. All of these behave similarly. They all light up and glow when you pass an electric current through them. None of them are really excited about making bonds, things of that nature. So chemical properties line up in columns, and we call those columns families. You can either name the family by the first element at the top, so this would be the fluorine family, or you could name it by the number of the columns, so this is family 1 and family 2, and then these are a little weird, family 3, 4, 5, 6, 7, and 8. Or you can, some of them have like other names that the group has been given. These are the alkali metals. These are the alkali earth metals. These are, you know, the noble gases and the halides and things like that. You'll learn some of these names as we go. But all of that to say that elements in a column generally behave like other elements of that column. The chemical properties line up. Okay. Now we're going to get to electron orbitals. The last lecture was on orbitals, and there was a lot of confusion when we were done. Because 1s and 2s and 2p and 3s and 3d and 3p and 4f, none of that made friends with you. But hopefully now you will start to make friends with this. The table shows us the outermost electron orbital that the element has. If it is in the first 2 columns of the table, or it's helium, because helium is small. If it's in the first 2 columns, then the element has an s orbital as the outermost energy level. Something s is going to be the end of the line. Okay? So hydrogen has 1s, and so does helium, 1s. And then lithium and beryllium have 2s. Sodium and magnesium have 3s. Potassium and calcium, 4s. Rubidium and strontium, 5s. And you see how this goes. Cesium and barium, 6s. Francium and radon, 7s. All of these end in the s orbital. If it is in the, what we call main group of elements, these guys over here, then it ends in a p. So it has s's and it has p's. Okay? If it's over here, then the last group is a p. So barium, sorry, just kidding, boron, has the s orbitals, 1s and 2s, but they're not the end of the story. The outermost layer is going to be a 2p. Same story for carbon, nitrogen, oxygen, fluorine, and neon. They will all end in 2p. That's going to be the outermost energy layer. And then sodium and magnesium start with 3s, and then here, aluminum, silicon, phosphorus, sulfur, chlorine, and argon all end in 3p. So you can see how this works. The energy configurations you can read straight from the table, right? These guys all end in a d orbital. That's the outermost layer that they have. So let's pick one, iron. Iron has 1s, it has 2s, it has 2p, it has 3s, it has 3p, and it has 3d. And iron, cobalt, nickel, copper, zinc, and all of its friends in this first row are going to have 3d. And then now, the ones that we hang out down on the bottom of the column end in the f orbitals. So you can see the reason the periodic table is arranged the way that it is, and the reason they cut these guys out from this line and said, no, we're going to hang those out down here, is not only to make the periodic table shorter and easier to print on a page, but all of these end in the same electron level, the kind of orbital. So S's, P's, D's, and F's. And now when you look at a periodic table, you can automatically read the electron orientation or electron configuration. Okay? Oh, and I have callouts that say the same thing I've already been saying. It's groups 1 and 2 only have s orbitals. Groups 13 through 18, or columns 13 through 18, these guys have p orbitals. And groups 3 through 12 finish in d. And then the 2 series below, the lactonide and the actinides, end in an f orbital. Okay? The rows of the periodic table give you the electron energy level of each atom. So, hydrogen and helium only have the first energy level 1. The next one is energy level 2, and then energy level 3. And then over here, energy level 4, but then when you get here, you're reading 3. It's kind of a little bit confusing. It has to step down 1. So energy level 1, energy level 2, energy level 3, energy level 4 here, and 4 here, but this middle column is shifted down 1 in the numbering. This is still the 3rd energy level. So in your brain, just know that you start counting this middle column from 3. And then this is 4, and 5, and 6. But down here, it's 4 and 5. So while this says 4, when you shift into the next area, it's down 1, 3. And the same thing is true here. This is 5, this is 4, and so is this. This is 4. So as you read across, you have to keep track in your mind that this starts at 3 and this starts at 4. But otherwise, 1, 2, 3, 4, 5, 6, 7, and then straight across here, this lines up with 2, 3, 4, 5, 6, and 7 in theory. So you can pick any element on the table. Pick sulfur. And I ask you what electron orbitals are present in sulfur. And you say, well, it has 1s, it has 2s, it has 2p, it has 3s, and it has 3p. That's sulfur's electron configuration. Let's pick tin. Tin has 1s, 2s, 2p, 3s, 3p, and 3d. So you just read through the table, and you get the electron organization for any element you pick, okay? What is it for? I don't even know many of these off the top of my head down here. Americanium. Americanium, number 95, has 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 5d, 4f, 6p, 7s, 6d, 5f. It's got a lot of different electron configurations. But all you have to do is just read straight across the table and know these are S's, these are P's, these are D's, these are F's. And you can read the electron orientation for any element on the table. Okay, this is going to be a homework assignment next week, is to write out the electron configurations of elements. But all you've got to do is just read straight across the table. You see what I'm doing? No. Do another one.
Can you explain what you're doing?
Yeah, so anything that, all of these elements end in an S orbital. All of these elements end in a P orbital. All of these elements end in a D orbital. All of these elements end in an F orbital.
So are you saying like the bottom is SPD? Are you saying you're reading down and I have to
You're reading across, right? And then each row is a number, 1, 2, 3, 4, 5, 6, 7. So as we were talking about the different energy levels, there's 7 potential energy levels that an element may have. And in those different energy levels, there are suborbitals. This was the lecture on Monday. There's S orbitals, P orbitals, D orbitals, and F orbitals. And so to get to any element, you just read across the table. So potassium, what's the electron configuration for potassium? It has 1 S orbitals. It also has 2 S orbitals. It also has 2 P. It also has 3 S. It also has 3 P. And then it ends at 4 S.
So is it just 4 S or do you put 2, 3 SP?
It depends on what the question is. If the question is what's the outermost energy level, what's the outside of its shell, then you just look and you say it's in the 4th column and it's in over here, so it must be 4s. But if I ask you to list all the electrons that it has, then you need to read across the table and list everything that you read.
So what about the browns?
The D's, so cobalt has 1s electrons, has 2s electrons, has 2p electrons, has 3s electrons, has 3p electrons, has 4s electrons, has 3d electrons. Just read across and list the different things that you run across as you read across the blocks. Yes?
Can you write it out? Like you're just like
I'm reading. Yeah, you would just write those letters. Like here.
2s, then 3s,
Mhm.
4s,
Yep.
3d,
Yep.
So you wouldn't
and 2s and 3d. I mean,
So for sulfur, I'll pick another one for sulfur. If I were to ask you to list the electron configuration for sulfur, you start at the top. It has 1s electrons, 1s. It has 2s electrons, 2s. It has 2p electrons, 2p. It has 3s electrons, 3s. It has 3p electrons, and that's the row that it's in, so we stop.
so when do you use the one that you showed us in the lecture?
This is what I showed you in the lecture.
No,
The circle one.
The
Put all the
1s,
different
2.
drawings. Yeah, that was just to help you see them. But when I ask you to list the electron configurations, you don't need to draw them. I just wanted you to see what the shapes look like so that you know that they're not all rings like an onion.
Can you do one of the ones?
Yeah, these guys get very long, but yes, I can. So, uranium, element number 92, okay? Uranium would sit, if you were to take this purple thing and slide it up here where it goes, uranium is in this row, right? You know, it's in here, spliced in there. So you got to read across. So uranium has 1s, it has 2s, it has 2p, it has 3s, it has 3p. It has, now you do list it, even though this is 3, and I'll show you why in a little bit. You do still list 4s first. It fills the s's before it goes to 3d. Don't stress about that. Read straight across. 4s, okay? 3p, 4s, 3d, 4p, 5s, 4d, 5s, 4d, 5p. This is very long. And then I go over here. 6s, 5d. Now this guy slides in, 4f. 6s, this is really fun. 6s, 5d, 4f, 6p. I'm almost done. 7s, 6d, 5f, and then I'm done. 7s, 6d, 5f, and that is the electron configuration for uranium. Hugely long, but all you have to do is just read straight across and list what you see. Okay? It's huge, but that's because this is element number 92. There's 92 electrons, so it takes a while to tell you where they all are.
So you actually like go through each row.
Mm-hmm.
We have to memorize the numbers then.
No, yeah, well, I mean, all you got to know is SPDF, and then you just read across. Yeah?
But then for the brown, it's like that 3.
Right. Know that the brown starts at 3 and that the purple starts at 4. It's not that hard. The S's start at 1, right? The S's start at 1. The P's start at 2. The D's start at 3. The purple start at 4.
Why does it go to E?
It doesn't do any E's. I don't know why E makes people mad. Yeah.
So why did you go from 60 to 5?
Because that's the way it goes here. 6, where am I?
Just like you
6p,
put it on top.
6p. Oh, sorry, 6d to 5f. 6d starts here at actinide, right? And then this row slides in right here.
Oh.
6d, 5f, then actually it goes back to 6d. Don't stress. Just read. There's a brown one. 6d, 5f. Okay?
So it would be 60, 5, and 60.
Yeah, it's weird. Yeah, don't freak out about it. Just read. Just read. Yeah. I won't. Yeah, I won't make you do that. That's strange. I don't stress out about that. Just read straight across. Just keep reading straight across. Okay. Okay. Here is what it looks like a baby.
Yeah, you know, like,
What kind of freakish baby?
no, like, you know how a baby that's formed in the womb? Like a fetus? Yeah.
little ball.
Fetus is not
That
looks
looks
like that.
It looks
That's like Dragon Ball.
no, it looks like a bunch of baby tomatoes
Dragon Ball Z.
with a balloon on top.
Dragon
These-
Ball.
So this is tomorrow when we have the balloon activity. So we're gonna see, you're gonna make something like this. Tomorrow when we have the balloon activity, this is what chemistry did last year, and you'll see how we got this picture. But this is an attempt to look at all of the orbitals in one picture. So this balloon is supposed to represent 1s, this balloon is supposed to represent 2s, and then here's the 2p orbitals, and then this would be 3s, and here's 3p orbitals. And so if you try to look at it all together, this is another picture of all orbitals together. And we will try to reproduce this again tomorrow once I buy balloons. But I thought I had to do it. Yes, sir.
So there's going to be balloons in balloons.
Well, that's the magic of Photoshop.
We're not doing that.
tomorrow.
We'll play with that tomorrow. Yep.
You can put a balloon in a balloon?
Yeah.
Well, it's kind of crazy, but yeah. So this is the heart of how you can read the periodic table. Okay. Were you guys okay with this?
Sure.
Cool.
Last slide.
Amen. I like to hear that.